Okay, welcome everyone to the Tutte Colloquia. Today we're very happy to have Hamza Fawzi, who is joining us from the Department of Applied Math and Theoretical Physics at Cambridge University, where he is a lecturer. Previously, he completed his PhD at MIT in 2016 with Pablo Perillo. His research is in convex optimization and its applications, and today he'll talk about an application in quantum information science. Hamza.
Thanks a lot, David. Thanks a lot for inviting me. It's really a pleasure to give a talk here in this combinatorics optimization department. So I'll be talking about some work at the interface of optimization, semi-definite programming, and quantum information. So really, the main character of this talk, or the main object I'm going to be studying in this talk, is something called the set of separable states, which is a fundamental object in quantum information. And it's a convex set, and we'll be studying the properties of this convex set. So let me define what this convex set is. So okay, so the definition is kind of complicated if you haven't seen it before. So let me try to digest it. Or dissect it a bit. So it's a convex set that lives in the space of Hermitian matrices of size n times m. Okay, and it's defined as follows. So you take two vectors x in c to the n and y in c to the m. Okay, and you form the tensor product of these two vectors. So this gives you a new vector of size n times m. Okay, and then you do the outer product of this vector with itself. So that's x tensor y times x tensor y dagger. And then, so this gives you a Hermitian matrix of size n times m. That's positive semi-definite. It's also rank 1. And then you look at the convex hull of all this. Okay, so this gives you, this is a complicated convex set in the space of Hermitian matrices of size n times m. You can also check, because x and y are normalized the way they are, that the trace of any such matrix is equal to 1. Okay, so this convex set really lives in the affine space that's given in here. So the set of rows that have trace is equal to 1. And in fact, this is a full dimensional convex set in this affine space. So it's this convex set has dimension n square m squared minus 1. Okay, and the why is this why is this an interesting set? So this set is exactly the set of states of bipartite states that are not entangled. So outside this set, essentially you have entanglement, and inside this set you do not have entanglement. So that's really the motivation from quantum information, and I won't really say any more quantum information stuff beyond this. Otherwise we'll just be studying the convex geometry aspect of this convex set, how to approximate it, how to optimize over it, and so on. Okay, so I'm someone who is mostly interested in optimization. So the key question when I have a certain convex set that I'm interested in studying is, how do I actually optimize a linear function on this convex set? Okay, so this is the following problem. So I take a cost vector m. So that's something that lives in the same space as SEP. So that's a Hermitian matrix of size n times m. And I want to compute the following quantity. I want to maximize the trace of m rho. So that's the inner product in my space, where rho ranges over the set of separable states. Okay, so this is the optimization problem I'm interested in. So the first thing I just want to explain, I'm someone who has worked before getting into quantum information. I've worked a lot in polynomial optimization, and I just want to convince you that this optimization problem is nothing but a polynomial optimization problem. This linear optimization problem that you see here. So the reason is because we know, if I want to maximize a linear function on a convex set, I know that the optimal is always at an extreme point. And so the extreme points, I know exactly what they are. This is how I define my set. So this optimization problem can be written in the following way. So I'm maximizing over x and y, both live in the unit sphere, of the trace of m times x tensor y times x tensor y dagger. And so now if I kind of unfold this trace that I have, okay, this is nothing but a polynomial in x and y. It's a polynomial of degree 4. And the coefficients are given by these mij, kn. Okay, so really what this tells us is that the problem of optimizing a linear function on the set of separable states is exactly the problem of optimizing a certain polynomial. It's a Hermitian polynomial. It depends on x and x bar, but the output is always a real number. So that's why it's a Hermitian polynomial on a product of two spheres. Okay, so here x has to live in the sphere, y has to live in the sphere. So really my feasible set is a product of two complex spheres. Okay, so really the question of representing SEP or solving a linear optimization problem over SEP can really be tackled using tools from polynomial optimization. And so this is what I'm going to do today. I'll try to understand these various computation questions on SEP from the lens or from the point of view of someone who does polynomial optimization. Okay, so let's actually talk about polynomial optimization on the sphere as studied by the optimization community. So so here I just have one sphere, and I'm working I'm working with the real polynomials, but really the story is going to be the same for complex polynomials. So what's a general polynomial optimization problem on the sphere? So I have a polynomial P of x1 up to xn, and I want to maximize this polynomial subject to a sphere constraint. So this is an NP-hard problem in general. So Nesterov showed this, and really, so the reduction comes from the fact that you can, so you can formulate the stable set problem. So the problem of finding the largest stable set in a graph, you can write it as the problem of maximizing a cubic on the sphere. This is something that was shown by Nesterov, and it's really an application of something called the Motzkin-Strauss formulation of the stable set problem, which tells you that 1 over the stability number of a graph is can be written as a maximization of a certain quadratic on the non-negative orthant, essentially, something like that. So stable, the NP hardness of stable set allows you to show that optimization on the sphere is NP hard. Another kind of nice instance of polynomial optimization is the problem of computing norms of matrices. So if you want to compute the 2 to 4 norm of a matrix, that can be written as the problem of maximizing a degree 4 polynomial on the sphere. Okay, so that's another kind of standard optimization problem. So, okay, so because of the NP hardness of polynomial optimization, it's not surprising that designing membership in this convex set, the set of separable states or non-entangled states, is hard in general. Okay, designing membership is NP hard, optimizing a linear function, and so on. These are all hard. And so the way out is really to try to find a relaxation or an approximation of this convex set that is tractable. Okay, and so perhaps the most famous relaxation, semi-definite relaxation of SEP is something called the PPT relaxation, the set of states that have a positive partial transpose. So this is something that has been introduced in the quantum information literature a long time ago, so from the 60s or 70s. And so let me kind of explain what this relaxation is about. So I'm first going to introduce the transpose map. So this is a map that takes an m by m matrix and outputs the transpose of this map. Okay, so this is just a linear map. And so the set PPT is a set that's also it's a convex set in the set of Hermitian matrices of size n times m. Okay, and it's defined as follows. So it's the set of rows that are positive semi-definite and trace is equal to 1. So these are obvious conditions that are satisfied by anything in SEP. And but it also the additional requirement that we include here is that the partial transpose of rho is positive semi-definite. And by partial transpose, I mean that if you apply this linear map, so identity tensor T applied to rho has to be positive semi-definite. So the way you can think of this is as follows. So if you think about rho as a matrix, so it's an nm by nm matrix, and if you think about it as blocks of size m by m, so various blocks of size m by m, this partial transpose operation, what it does is that it transposes each of the blocks. Okay, so you do this linear operation on the blocks, and you require that this is a positive semi-definite matrix. Okay, it's very easy to check that SEP is actually included in PPT. So you just have to verify this on the extreme points of SEP. And so if you apply identity tensor T on XX dagger tensor YY dagger, what you get is that you're going to transpose this second slot that you see here. And so you get Y bar dagger, and this is positive semi-definite as it's the tensor product of two positive semi-definite matrices. Okay. And so, okay, so we get this relaxation of the set SEP. That's an efficient relaxation. It has an SDP description. So that's kind of efficient. So you can efficiently optimize a linear function on PPT or efficiently decide membership. But unfortunately, I mean, the SEP and PPT only agree in the very low dimensional cases. So whenever n plus m is less than 5, it was shown in the 60s or 70s that that SEP is equal to PPT. Otherwise, for other values of n and m, these two sets are distinct. Okay. So, so this is the kind of the most popular or the most well-known maybe relaxation of the set of separable states. So I would like to kind of explain because I mean, coming from a polynomial optimization background, the set PPT actually has a very nice interpretation or explanation in terms of certain polynomials being sums of squares instead of being non-negative. So I'd like to introduce this this explanation of PPT, where this set PPT actually comes from. So let's recall, this is how SEP is defined. I mean, this connection will go through duality, and so duality of convex sets. So remember that whenever I have a convex set, the dual of the convex set is exactly the set of linear forms that are non-negative on the convex set. Okay, so for example, if this is my set SEP, SEP star, the dual of SEP, is exactly the set of m's such that the trace of m rho is non-negative for all rho in SEP. Okay, so I can equivalently rewrite this condition as this is exactly the set of m's such that Pm of xy is globally non-negative, so meaning it's non-negative for all x and y in Cn times C to the m, where Pm is the polynomial I've introduced before. It is the degree 4 polynomial in x and y that's defined with the coefficients mi, j, k. Okay, so here I just rewrote the definition of what this means to be non-negative. I just expanded the definition of trace of m rho when rho is an extreme point of SEP. Okay, so SEP star is really should be thought of as a family of polynomials that are globally non-negative. Okay, so it's, you look at the set of polynomials of this form, and you look at the ones that are globally non-negative, and that's exactly the dual of SEP. So it turns out that the dual of PPT is exactly the set of m's such that this polynomial Pm is a sum of squares. Okay, so this means that it can be written as a sum of squares of Hermitian polynomials. So so a Hermitian polynomial is a polynomial that takes complex variables and always outputs a real number. Okay. So PPT star is exactly the set of m's such that Pm is a sum of squares. I mean, I will not show this, but this is something that you can actually prove. Okay, and so the inclusion, this diagram really summarizes the what we have. I mean, we have SEP is included in PPT, and by duality, PPT corresponds to polynomials Pm that are sums of squares, and SEP corresponds to polynomials Pm that are non-negative, and so we have the reverse inclusion in this and the dual level, at the level of dual sets. Okay. So I'm saying this early on here because the distinction between sums of squares and non-negative polynomial will be kind of crucial in the other results I will present in this talk. Okay. So really, just to summarize that the distinction between SEP and PPT is exactly the distinction between non-negative polynomials and sums of squares. In fact, this is one way you actually show that SEP is different than PPT for high values of n and m, is that you exhibit a certain polynomial of this form, and you show it's non-negative but not a sum of squares. For example, if you want to show that SEP of 3, 3 is not equal to PPT, there is a polynomial that was exhibited by Choi, which shows that which is non-negative but not a sum of squares. Okay, so so what I'm going to study, so we've seen that SEP and PPT disagree as soon as n plus m is bigger than 5. So the first question I'm going to consider in this talk is, can we hope to have a semi-definite representation of SEP of nm whenever n plus m is bigger than 5? So by this I mean a semi-definite representation that's different from PPT, so something that is more complex maybe or more general. Okay, and I'm going to show that the answer is no, and that as soon as SEP is different than PPT, then there is no SDP representation of SEP. And in the second part of the talk, so it will be a bit shorter, I'm going to talk about more positive results. So about a certain hierarchy of SDP relaxations and how fast does the hierarchy converge to the set SEP, okay, the convergence of the hierarchy. Okay, so let's maybe let's go into the first part. So I first need to explain what I mean by an SDP representation. I really did not define this. I think many of you already know what this is, but it's good to define things so that we're on the same page. So a semi-definite program is an optimization problem of the form where I want to maximize a linear function subject to a linear matrix inequality. So A of x is linear or it's actually affine in the x size. Okay, so that defines a convex set. And I've seen that I've already said that linear optimization on PPT is a semi-definite program. So I say that a convex set C has an SDP representation if I can write it as in the following form as the image of a certain convex set S that is described using a linear matrix inequality. Okay, so S is called, I mean, in the SDP literature, it's called a spectrahedron. Okay, so S is the set of x's that make A of x positive semi-definite. So that's a convex set that you see upstairs. And I say that C has an SDP representation if it can be written as the linear image of such a spectrahedron. Okay. I mean, if this is something that you've seen before, then I mean, this is good. It may sound natural, but I mean, if you haven't seen this before, maybe let me just say that having this linear image is actually very important and gives you much more flexibility in describing convex sets. What I mean by this is that there are certain sets, you can show that there are certain sets that do have an SDP representation of this form, but can never be written as a solution set of a linear matrix inequality. Okay. So maybe this is one example. I'm not going to prove it for you, but it's actually not so difficult to prove. I can maybe explain later if someone is interested. So if you just take the following L4 ball, so the unit ball of the L4 norm, so just the set of xy such that x to the 4 plus y to the 4 is less than 1. That's a very nice convex set. It has an SDP representation, so you can write it as the projection of some S, and S is defined using an LMI and so on. But you can show it's not a spectrahedron, meaning that I cannot write it as the solution set of a linear matrix inequality. What I mean by this, I really need the projection step. Okay, and the important thing here is that if my convex set C has an SDP representation, then I can still optimize a linear function on C using semi-definite programming. I just need to go to the higher dimensional space. So I need just to compose my cost function L of x by the projection pi. So really the minimum of L of x on C is really just the minimum over my higher dimensional set S, which is defined by A of y is positive semi-definite, of L composed with pi of 1. Okay, so this guy on the right hand side is a semi-definite program, so I can actually optimize over C efficiently. Okay, so this is the definition of SDP representation. I mean, okay, I won't really talk a lot about the lifting aspect from the complexity point of view, but I mean, I've given here one example where lifting is important from just the point of view of existence of a semi-definite representation with this L4 ball example. But you can actually show also that there are examples of convex sets that if you do not allow for lifting, the complexity is very high, and that going to a higher dimensional space allows you to reduce the complexity significantly. Okay, there are very classical examples like the permutahedron, which has an exponential number of facets, 2 to the n facets, but you can write it as the projection of the set of permutation of the convex hull of permutation matrices, which has a polynomial size description. So the set of doubly stochastic matrices. And another classic example is the stable set polytope of perfect graphs, which Lovash shows has an SDP representation using the theta bodies and so on. Okay, but I will not go into the detail in here because this section I'm mostly interested in existential question. Yeah. So the question of which convex set. So this is really my definition of SDP representation. It's a very natural definition of SDP representation if we care about semi-definite programming. I mean, which optimization problem can I formulate as semi-definite programming? So a natural question that was considered in the optimization literature is which convex sets actually have an SDP lift? Okay. Which convex sets can I write as the projection of some set defined using an LMI? By LMI, I mean a linear matrix inequality. So there is one kind of necessary condition that is somehow obvious, which is that the set C has to be semi-algebraic. A set is a set is semi-algebraic if it's defined essentially just using polynomial inequalities, equalities, and you're allowed to take any Boolean combination of such conditions. And it's almost obvious that a convex set any set C that has an SDP representation has to be semi-algebraic. The reason is the condition that a matrix is positive semi-definite can be encoded using polynomial inequalities. Okay, so you essentially require that some minors of the matrix have to be non-negative. Okay, and then you use actually a non-trivial result that if you take a semi-algebraic set and you project it, then you still get a semi-algebraic set. Okay, this is a result due to Tarski and general quantifier elimination. So yeah, that's okay. So any set that has an SDP lift must be semi-algebraic. So Nemirovsky actually in 2006 he asked the question whether any convex semi-algebraic set has an SDP lift, has an SDP representation. So Bill Helton and Zhawang Ye in 2009 they released kind of a series of papers where they gave sufficient conditions for actually this to be true. So they showed, for example, that if the boundary of C is smooth enough, so the boundary of my convex set is smooth enough and has positive curvature, then the convex set has an SDP lift. I mean, they have some couple of results but they're all in the same direction, same flavor. And they actually conjectured a positive answer to Nemirovsky's question. And this then kind of became known in the community as the Helton-Ye conjecture, that any convex semi-algebraic set has an SDP lift. So Klaus Schreider in 2012. So Klaus Schreider is an algebraic geometer in Germany in Constance, who became interested in these questions of SDP representations and so on. So he showed actually that the answer is yes if the convex set is a two-dimensional convex set. Okay. So he showed that any convex semi-algebraic set in the plane has an SDP lift. But actually later on he showed that the answer to the Helton-Ye conjecture is false essentially, and that you have many convex semi-algebraic sets that do not have an SDP representation. Okay, so what I would like to show, I mean, in this first part of the talk is I would like to actually reprove Schreider's, and to show that the set of separable states is one such example of convex semi-algebraic set that does not have an SDP lift. And essentially, we will show that as soon as SEP is different than PPT, then the set of separable states has no SDP lift. Okay, so in other words, I just need to show that the minimal cases, SEP of 3,3 and SEP of 4,2 have no SDP lift. Okay, it's obvious. I mean, no, it's not obvious, but you can show that the set of separable states is a semi-algebraic set using all the Tarski's quantifier elimination result. Because it's the convex hull of a semi-algebraic set, so it is a semi-algebraic set. Okay, so this kind of gives another counter example to the Helton-Ye conjecture, and in fact, so the proof I'm going to show is fairly elementary. I mean, it uses some results from about semi-algebraic sets and functions and so on, but other than that, it's fairly elementary and easy to read. Yes, and I hope I'm going to present it in the next 15 minutes or so. So maybe before I get into the techniques of the proof, are there any questions or anything?
Hamza, I have a question.
Yeah.
if the set SEP NM had an SDP lift, would that have implications for complexity theory?
So it depends on the size of the lift, right? So I mean, it depends on two things. So I mean, so the complexity of solving semi-definite programming is still not completely settled. You know, I mean, if you apply the ellipsoid method, you have this big R and the little r kind of thing that we cannot bound exactly. So you need to show that your SDP is actually a nice SDP in the sense that you can actually bound I mean the radius of this set S, and then obviously the size of the SDP has to be small. I mean, so it's not inconceivable, for example, that SEP could have an SDP lift of size, I don't know, 2 to the n or something like that.
Thanks.
I have a question too. Hi. I was wondering about these polynomials that show that when n plus m is greater than or equal to 5, or is greater than 5,
Yep.
that the two sets are distinct. Do these polynomials imply a bound entangled state that one can write down?
A bound entangled state.
The bound
I do
entangled
not know actually what this is. So
the bound entangled states are basically states that live in PPT but not in SEP. It's a little more general than that, but all such states are bound entangled. And that's how the Hordetsky's, which is the first I knew these sets were different, had showed it.
yes.
But you seem to have found a much earlier reference, and I wonder if these imply some interesting states.
Yes, so they actually work. I mean, these polynomials really work in the dual set. So they show that there is an element in the dual set of one, which is not in the dual set of the other. But by duality, one can construct, I mean, a separating hyperplane in the primal space. But I do not know if there is an explicit. I mean, the history, I forgot exactly how. I mean, which was proven first. I mean, if the two sets were distinct in the primal space or in the dual space, I do not know what happened first. But there is a kind of I mean, a paper of Choi on positive biquadratic forms where he gives an explicit polynomial, and the other paper by Volnovich where he actually gives this explicit polynomial. Yes, but I do not know if in this paper they actually derive the separating hyperplane in the primal space.
Well, that's interesting.
Mm-hmm.
Even if it's not relevant to the history, it'd be interesting if these polynomials give particular states of interest.
Yeah, they should give. Yes, yeah, they should.
And if they're equivalent to other ones that have already been discovered, or if they're a new class, I'm going to look into that.
Yes, this I do not know. Yeah, that's.
Thank you.
Question? Yes. I had a question, which is that is the dual of the SEP entanglement witness?
Yes, yeah, that's exactly what it is. Yeah, I mean, in the quantum information, parlance, yes, that's exactly. I mean, it's separating hyperplane, yes. So it's
right. And then to John's point, which is that if you find entanglement witnesses, that's one way to pull out bound entangled states usually. But that's a comment. Okay, thanks.
Okay.
Yeah. Question.
Yes.
So are these SDP lifts what people sometimes call spectrohedral shadows?
Yes, that's the same thing. Yeah.
That's the same thing. Okay, thanks.
Okay. Okay. Okay, good. So maybe let me go with the proof. So I'll try to kind of let's see. Yes, so the proof goes through some. I mean, the question of studying SDP representations and so on has been a kind of an active field for the past 10 years or a bit less. So there's some machinery that has been developed to actually study this. So I'll try to kind of introduce some of this machinery, but I hope so let's see how it goes with time. So I mean, the first thing that actually we usually do when to study the question of whether an SDP lift exists or not is to consider something called the slack matrix of the convex set, so which is kind of an algebraic way of thinking about an SDP lift. So the definition of SDP lift is kind of hard to work with. It's kind of geometric and so on. the slack matrix is an algebraic way that's much easier to handle. And so it's a way to actually associate with our convex set C a big matrix, okay, called the slack matrix, and it's defined as follows. So one side of this matrix is indexed by all extreme points of my convex set, and the other side is indexed by, if you want, extreme points of the dual, or separating hyperplanar. I mean, if you want, supporting hyperplanes of my convex set. And what I do, so I mean, if you look at this picture, that's a polytope, and I have a certain supporting hyperplane L, and I have an extreme point X, and at the XL entry of my matrix, I just put the slack of the extreme point X with respect to the supporting hyperplane L. Okay, so this gives you a number L of X. That this number has to be non-negative because L is a supporting hyperplane. And this is just the matrix. Okay, so this is my matrix. I mean, if C is a polytope, then this matrix is finite, but in general, this is an infinite matrix. So this matrix has non-negative numbers, and one can show the main kind of takeaway message from this slack factorization theorems is that finding a semi-definite representation of C, or the existence of a semi-definite representation of C, is equivalent to a certain factorization of my slack matrix S. Okay, so the actual statement of the result is of this equivalence, it goes as follows. So my convex set C has an SDP lift of size n if and only if I can find certain maps A. So A goes from rows to Hermitian matrices that are positive semi-definite, and B goes from the columns to Hermitian matrices that are positive semi-definite, such that I can write S of XL as the trace inner product, the trace of A of X times B of L. And this has to be true for any row X and for any column. Okay, so this, I call this an SDP, PSD factorization of my slack matrix. And the result is that there is an SDP lift of size n if and only if my slack matrix has a factorization of this form. Okay, and the size of the SDP lift is exactly the size of the factorization, the size of this matrix. So this theorem is kind of looks very surprising the first time you see it. From the technical point of view, actually, if you look at the proof, it's not so long. It's kind of a clever application of Farkas lemma, really. This is what happens. So I will not prove it here. And there's actually a version of it that's that has to do with the linear programs or polytopes that was proved by Yanakakis in '91. So, and this is an extension to SDPs. So okay, so this is what I'm going to use, and in fact I'm going to use a certain special case. I mean, a certain small corollary of it. So the idea here is that since A of X and B of L are positive semi-definite, I can really write these guys A of X as certain FF transpose, and I can write B as GG transpose, right? So so then I get the trace of FF transpose times GG transpose, and so this is really. I mean, if you look at this line here, so I write A of X as F of X times F of X transpose, and G of L times G of L transpose. So this is really just a certain a sum of the squared entries of this matrix F of X transpose G of L. Okay, and so really, if you just do the analysis, I mean, really just this line, if you analyze what's happened here, is that if your set C has an SDP lift of size n, then what you get is you get a subspace V of dimension at most n squared. So V is a space of functions on X. So it's really the space spanned by the entries of big F of X here. Okay, such that for any supporting hyperplane of my convex set, okay, I can write L as a sum of squares from of functions from this subspace V. Okay, so again, this subspace V. So this is exactly what you get here. Right, so this Frobenius norm squared of this matrix, each entry of this matrix is a linear combination of the entries of F of X. Okay, and so really each HK is a linear combination of the entries of F of X. So my subspace is just the span of all the F of X. Okay, so this is really the main thing that I will need to prove my result. So yes, so this is really the same. This is really the result I want to prove. I mean, the non-existence of an SDP representation but stated in a slightly simpler case of not exactly the set SEP, but sets that look very similar, very similar to SEP, and sets that only involve real variables and so on. What I really want to emphasize, maybe before going through the statement here, is that what we're going to show is that, I mean, for any polynomial p that is non-negative but not a sum of squares, I will be able to construct a certain set, which is described in here, a certain convex set that I am going to show will not have an SDP representation. Okay, so for any such polynomial, and in particular, the application to SEP will come from taking P to be this Choi polynomial I mentioned before, this will give me the case of SEP of 3,3, and the set SEP of 4,2 will correspond to taking P to be this polynomial of Voronov. Okay, but I just want to kind of state the theorem in the real case, because it's kind of allows me not to worry about some other technical details in the complex case. So really, the idea is I start with a polynomial P that's non-negative but not SOS, and then I define a certain set of monomials, okay, of power of powers really, and then the claim is that this convex set CA has no SDP representation. So I just want to emphasize again that this set CA has a very similar flavor as the set of separable states. Really, the set of separable states is also a convex hull of certain powers of x and y, so which are xi, xj, yk, yl. Okay, so it's really of this form exactly for a certain well-chosen set. Okay, so let me now explain how do we prove this theorem using the slack matrix formulation I said before. Okay, so the first thing to understand, let's try to understand what is the slack matrix of this convex set. Okay, and to do this, I need to understand what are the linear functions that are non-negative on this set. Okay, it's just one moment of thinking tells you that really, if you take a linear function that's non-negative on CA, that's in one-to-one correspondence with polynomials that are non-negative and supported on this set A. Okay, because if you write what's a linear function on this convex set, so what's a linear function that's non-negative on this convex set, it's exactly, it gives you a polynomial supported on A that's non-negative. Okay, and so if I rewrite my theorem about existence of SDP lifts using sums of squares, it really tells me that CA has an SDP representation if and only if there are certain functions, so these functions are the ones that span my subspace, such that any non-negative polynomial supported on A can be written as a sum of squares of functions from the span of these functions. Okay, this is, and K is actually going to be related to the size of my SDP representation. So this is precisely the statement I showed 2 slides ago, but specialized to the case of CA. Okay, so there is one kind of technical detail that is important here, and that is actually the main thing that allows me to prove this result, is that one can actually show that these functions fi can be taken to be semi-algebraic. So semi-algebraic functions are those functions that have a graph that is a semi-algebraic set. So all power functions and so on, these are all semi-algebraic functions, and non-semi-algebraic functions are things like the exponential, cosine, log, and so on. Okay, so in order to get this one needs to invoke some Tarski's result and so on, but these are fairly, again, natural things to, I mean, it's natural to think that these functions are going to be semi-algebraic. Why would you need an exponential or a log or something like that? Okay, and why is this important is because semi-algebraic functions are tame, so they have, they cannot be kind of very wild, and you can show that they actually are smooth almost everywhere. So they can only be, they can only have singularities. The set of singularities can only have a measure 0. And this is something that will be crucial in the proof here. So how does the proof go? So assume that my set CA actually has an SDP representation. So I can I have my F1 up to Fk. These are the semi-algebraic functions associated with this representation. So this means that any non-negative polynomial supported on A has a sum of squares from the span of these functions. Okay, And since the Fi are smooth almost everywhere, and since I only have a finite number of such functions, I'm going to assume, I can assume that these functions, by translating everything, I can assume that these functions are actually smooth at the origin. Okay, so now what I have, what I have is I have certain functions fj that are smooth at the origin. And remember that I started with a polynomial p that is a non-negative but not a sum of squares. Okay, let's assume for a second that this polynomial p is homogeneous. Okay, so all the monomials have the same degree. Okay, then you use this simple lemma to actually conclude the argument. So if you have a homogeneous polynomial p that's a sum of squares where the functions under the square are all c infinity at the origin, then you can show that p is a sum of squares of polynomials. Okay, so the functions fj a priori were not polynomials, but you can show that if the fj are actually smooth at the origin, then this has to be a sum of squares of polynomials. And this contradicts my first assumption that p was a non-negative polynomial that's not a sum of squares. So this really concludes the proof. If we assume that p is homogeneous, when p is not homogeneous, you need a certain additional technical argument that is not I'm not going to talk about here. But this is really, I mean, just to recap the proof is that you assume your set has an SDP representation. We know that the linear, non-negative linear functions on this set are exactly non-negative polynomials non-negative polynomials supported on this set A. Okay, but because I started, in fact, with a polynomial p that is not a sum of squares, okay, I reach a contradiction. Okay, because the existence of an SDP lift will imply that this polynomial has to be a sum of squares of polynomials. So it's really kind of the proof is really not very complicated. So in at least for the case of homogeneous polynomials, there's, as I mentioned, kind of some technical arguments needed for the general case. So let's go back to the set SEP. So to deal with the case of SEP, we need to work with Hermitian polynomials. Okay, but this is fairly standard. It's not kind of super interesting, but you just need to kind of think about polynomials in the variable and its complex conjugate. And then, as I mentioned before, if SEP of NM is different than PPT, we know that there is a certain polynomial that's non-negative but not a sum of squares that certifies the distinction between the two. And so for SEP of 3,3, I use the Choi polynomial, and for SEP of 4,2, I use a polynomial that's by Volnovich. And I use some of its properties studied later by Ha and Ki. Okay, so this is actually this is really just the proof of the theorem that I wanted to say. I mean, that shows that the set of separable states has no SDP representation in general when n plus m is bigger than 5. So okay, so I want to kind of move in the last maybe 5 or 10 minutes to a more positive aspect. So I want to study what happens now. Okay, I cannot represent SEP exactly using SDPs. Can I approximate it, and if so, what's the convergence rate and so on? But maybe before I do so, are there any questions about the proof or?
So one question.
Mm-hmm. Yes.
Did you explain why the dual of PPT set is a sum of squares?
No, I did not explain this. It's kind of so it's written in the paper the proof. It's I think it's something that's kind of agreed. I mean, I really did not find a full proof in the literature, so that's why we put a proof. But I mean, many people are aware of it. I mean, people that I talk to and so on. But yeah, it's in the paper. I mean, there's a full proof. It's not so difficult to prove.
Got it. Thanks.
Any other questions or? Okay, maybe I will go to the hierarchies of relaxation. So we've seen that. I mean, again, I like to work in the dual side because it has to do with polynomials and so on. So so we've seen that the dual of SEP are exactly polynomials that are non-negative. The dual of PPT are polynomials that are sums of squares. Okay, and we know that these guys are distinct when n plus m is bigger than 5. So so in the polynomial optimization literature, there is a known way of how we can improve this sum of squares relaxation. I mean, so if a polynomial is not a sum of squares, I can try to write it as a ratio of sum of squares. Okay, and so this is how the so-called DPS hierarchy can be defined. I mean, even though this is not at all, I mean, not the usual way it's defined, but you can define this hierarchy as the set of the dual of DPS as the set of n, such that this polynomial Pm can be written as a certain sum of squares divided by this particular polynomial that's a square, which is the Euclidean norm of y to the power 2 times n minus 1. Okay, so clearly, if this guy is a sum of squares, then Pm has to be non-negative. Okay, so this means that DPS L star is included in SEP star. Okay, and actually, so in the if I go back to the primal space, I have these inclusions that SEP is included in PPT, and PPT is exactly equal to DPS1. I mean, if you just plug in L is equal to 1 here, but in general, DPS1 is included in DPS2, and so on and so forth. Okay. So okay, I think I messed up the inclusion. So you should get tighter and tighter relaxations. I think it should be the other way around. Sorry, it's so as you increase L, you get tighter and tighter relaxations of the set SEP, and what you would like to get is what you hope is that as L goes to infinity, that DPSL actually converges to the set SEP. And so you can note that the set DPSL has an SDP representation of size roughly d to the L. So we know actually that there is no finite L for which DPSL is going to be equal to SEP, but what we would like to have is hopefully is that DPSL will converge in a certain way to the set SEP as L increases. Okay, and so as I mentioned before, the set SEP and the set SEP really has to with polynomial optimization on the sphere, and so such results actually can be derived or are very similar to results that have to do with the with polynomial optimization on the sphere, the general polynomial optimization, and how does the sum of squares hierarchy behave. So this is something that we prove with Kuhn, who is now at Waterloo, as I mentioned. So we show the general convergence result for the sum of squares hierarchy on the sphere. So if you want to just minimize a polynomial on the sphere, or just certify that the polynomial is non-negative on the sphere. So I mean, this is one statement that we have. I mean, if P is a polynomial that's non-negative and at most 1 on the sphere, we cannot hope that P is going to be a sum of squares. I mean, there are examples of polynomials that are non-negative but not a sum of squares. But what we can show is that if you add a small constant to it, so if you add a certain that only depends on the degree of n times d over L squared, okay, that this new polynomial here is going to be LSOS. Okay, so LSOS means means that essentially if you pre-multiply it by the norm of x squared, but to the power L, it's going to be a sum of squares. Okay, so meaning that it lives in the it means that the Lth level of the sum of squares hierarchy will be able to certify a minimum yes, a minimum of minus Cn times d over L squared. Okay, so this, I mean, this result, the best previous result gives a convergence in d over L instead of d over L squared. Okay, so this result with Kuhn improves on the previous result when L is larger than d, which is the regime that we're interested in here. And actually, so one can apply, I mean, the same machinery that we use to prove this result can be applied to get bound on the convergence of the DPS hierarchy. And so this is what we can show. So HC here of M is the, if I have a certain matrix M, that's the maximum of trace of M rho where rho C. And so we can get kind of, we can show that if you optimize a linear function on the level of the PS, then you get close to H-sep to within by Navasquez, Owaria, and Plenio in 2009. Whereas our proof is actually completely based on sum of squares considerations. So I actually wanted to kind of give you an idea of how the proof works in just 2 slides. So I'll actually conclude by this. So how do we prove a result like this one? If I take a polynomial p that's non-negative and I want to show that if I perturb it a little bit, it's going to be a sum of squares. So I just want to present the main idea and without the technical details. So the setting is as follows. I take a quartic, so a polynomial of degree 4, let's say, and it's non-negative on the sphere. And the goal is that I want to write p as a sum of squares. So I know this is not going to be possible in general, but I hope that if I add a certain constant to p, then this will allow me, I will be able to do this. So the main idea to do this, and as I'm going to mention later on, this idea is not new. I mean, in fact, it was used by Resnick and so on. I will explain later on. Is to define something called an integral transform. Okay, so something that takes p and outputs a new function on the sphere, and it does so by doing a certain convolution of p. So essentially integrate on the sphere. So phi here is a univariate function. So integrate over all y in SD minus 1 of phi of x transpose y times p of y d sigma of y. And sigma here is the probability measure on the sphere. So you can see that if phi is a Dirac delta at 1, what you will do is that you will exactly pick out the y is equal to x. So you will just get that kp is equal to p. So this will be the identity operator. Okay, this is one, the first observation. The second observation is that if my function phi of t is a square, so let's say it's h of t squared, where h is a degree L polynomial, then what I actually have is that I'm writing is that kp is actually going to be an infinite sum of squares, okay? Because p is now negative, okay, and these guys are squares. So I'm going to have that kp is actually a sum of squares, or an infinite sum of squares, but you can turn it into a finite one. So really the goal is really to choose a certain phi that's a square, but that also close to a Dirac delta. Okay, so if you do this, then you get that kp is LSOS, and kp is approximately equal to p because phi is close to a delta. Okay, so this gives you the high-level idea. To turn this into an actual proof, you need a little bit of Fourier analysis on the sphere to actually make this work. But you can make it work, and you can show that that p plus a certain constant c is going to be L sum of squares, where c is a constant that measures how close k is to the identity operator. So you can show that k diagonalizes in a certain basis, and essentially c just measures how the eigenvalues are actually far away from one. And by using certain well-chosen orthogonal polynomials, you can show that taking c to be d squared over L squared is a possible. It's something that p plus a constant times d squared over L squared is going to be L squared. Okay. So as I mentioned, this idea is not new. I mean, Resnick, his proof, even though it's really not written in this way, but it's equivalent to this. Resnick, which is a paper from '95. Uses the kernel phi of to t. Doherty-Venner kernel. A different kernel, but the Fourier analysis is a bit different. And as far as I know, what he told me is that this is method polynomial. So okay, so this is really the main idea of the proof. I mean, the more technical details are in the paper. So maybe just to conclude here is that there are, I think, a lot of exciting opportunities of using tools from polynomial optimization and semi-definite programming to solve problems in quantum information. And these are just two examples. This first archive paper contains the the non-existence of SDP lifts for the set of separable states. And the second one contains the work with Kuhn on the hierarchy of hierarchy for polynomial optimization on the sphere. So that's it, and thank you. I'm happy to take questions if you have any.
Thank you, Hamza.
Thank you.
Are there questions for Hamza?
Yes, one question. So is this D square over L square optimal? You cannot improve it or something?
No, we don't have any result that shows it's optimal. I mean, it's optimal for this technique. Can show that there is no way to choose the phi and so on that gives you something better than D squared over L squared. But I mean, this question of the convergence of the DPS hierarchy is it's not an easy question. It's been studied. I mean, I didn't have time a lot to mention the existing works, but there are some lower bounds based on complexity theoretic results, and we're very far from actually reaching this these lower bounds. No, I mean the problem is still very wide open about what's the actual convergence of DPS. Yeah. I mean, there are papers by Aram, Harrow, and so on lower bounds, Harrow and Montanaro, and so on lower bounds of the convergence.
Thanks.
No problem.
We have time for another question. If there are no further questions for Hamza, let's thank him again for a very clear talk. And